Alright, this is part 2 of section 10.3. We'll look a little bit shorter lesson, I believe. We'll look at arc length, and here's a theorem, 10.8, arc length in parametric form. If a smooth curve C is given by x equals f of t and y equals g of t, then such that C does not intersect on itself. So that previous one that we looked at, that prolate cycloid, that's not going to apply here, it wouldn't work here, but if it doesn't, then we can go ahead and on the interval from a to b, then the arc length of C over the interval is given by this. S is equal to the integral from a to b of the square root of the derivative of x with respect to t quantity squared plus the derivative of y with respect to t quantity squared. Or here's another way to look at it, and some of you might like this way a little better anyway. It's up to you. Okay, so let's go ahead on this example and say let's find the arc length of the following. And we've got x equals t squared, y equals 2t on the interval from 0 to 2. Well, really, all it looks like we need to do is be able to find the derivative of x with respect to t and y with respect to t, and then calculate an integral. So we've got s is equal to, the integral from a to b here is 0 to 2. Square root of, well, dx dt, that's not too tough, right? It's just 2t, that quantity squared, plus dy dt, quantity squared is simply 2 squared, which is, I'll write it as the same, 2 squared dt. So that is equal to the integral from 0 to 2 of the square root of 4t squared plus 4 dt. Okay. Now, you may or may not remember how to do that, and I'm guessing this is one of those kind of ugly ones that you could maybe notice we could factor out a 4 and pull that out as a 2. The square root of 4 is 2. We could certainly do that, but we're still left with something the square root of t squared plus 1 underneath that radical. So let's go ahead and look at the tables, and when you do that, you're going to find that this is equal to, in fact, let's go ahead and do that I talked about just a second ago first. If I pull the 2 out, it's going to look like 2 times the integral from 0 to 2 of the square root of t squared plus 1. And if you're not sure where that came from, take a look. Just take a look. Ask me later if you need a chance to take a peek at that. Okay, so this integral here is equal to, by the tables, 2, which is what we had up front, times 1/2 times the quantity t times the square root of t squared plus 1 plus 1 times the natural log of quantity t plus radical t squared plus 1 close that, bracket from 0 to 2. And if I go ahead and put those numbers in, 2 times 1/2 obviously is 1. Putting in the 2, I get 2 times the square root of 5 plus the natural log of 2 plus the square root of 5 and then putting in 0, that term goes to 0. The natural log of 1 is also 0, so there's my answer. Right there. Okay. So that's the arc length of this parametric equation, or of this parametric, and there we go. Now, if we had time, if I'm in class, we'll look at this example 5. I like that. I want you to read through it. It goes back to something we looked at earlier. Really, I think, an interesting problem. So take a peek at that one. Next, we move on to area of surface of revolution. And you can see, hey, this is kind of related to what we looked at before. And if you go back to what we learned earlier about surface areas, it's a very similar formula. What you want to notice here, though, is S is equal to 2 pi times the integral from a to b of g of t, now that's the y equation, times the square root of these two derivatives, quantity squared, when it's revolved around the x-axis. Okay. If it's revolved around the y-axis, we want this with terms of f of t. And so just pay attention to that. It's just remembering which one is which. Yeah, you'll have to come up with your own mnemonic to help you remember that. I don't have a great one off the top of my head. Okay. And you may look at it like this. The differential of the arc length, ds, is equal to this. And so then the formulas are written 2 pi times the integral from a to b of g of t ds, or f of t ds. So those are the formulas. Let's take a look at an example. So we might come back and peek at that in just a minute. It says, let C be the arc of the circle. X squared plus y squared equals 9. So that's this part right out here, just this part of the circle. Oops, excuse me. From 3, 0 right here to 3 halves, 3 times the square root of 3 over 2, as shown in this figure. Find the area of the surface as I rotate this around the x-axis. Okay. So a couple things, heads up before we get started. I know x squared plus y squared equals 9. I also know, you've seen the formula before, x squared plus y squared equals 1. If I've got a unit circle, then we talked about the cosine of theta, quantity squared, plus sine squared theta equals 1. Okay, when we've got that in mind, okay, then we can simply say, oh, that's kind of the same thing. That was a unit circle. Now we're just 3 units further. We're multiplying it by 3 in essence. And so as we move on to the next slide, you can see we can represent C parametrically by these equations. X is 3 cosine t. Y is 3 sine t. X squared plus y squared, if you wanted to look at that, would equal 1. And you'd get 9 cosine squared t plus 9 sine squared t equals 1. Let me see, I may have screwed that up. Hold on. Yeah, I just misspoke a little bit ago. If you solve this for cosine t, it would be x over 3. We get cosine t quantity squared plus sine squared t equals 1, and then you'd multiply, squaring both of those, you'd multiply by 9 to get that equation that we had. All right, here we notice our parameter is from 0 to pi over 3. You can find that by looking at that when t equals 0, x is 3, t equals pi over 3, x is 3 pi over 2. You're going to have to know that trig, and I know. Put your arms up in the air, you figure out where those things are. Just be aware of that. The trig just doesn't seem to go away ever. All right, on this interval then, C is smooth, Y is non-negative, and you can apply theorem 10.9, which is 2 points ago right here. This is theorem 10.9. Remember, we're going around this time the x-axis, so we're using this one. So we get 2 pi times the integral from 0 to pi over 3 of 3 sine t square root of the derivative of this base squared plus the derivative of this p squared. And look how nice that works out here. That we know that, of course, that this is equal to 1. The square root of 9 times 1 is simply 3. So we get this integral at the bottom, negative 18 pi times cosine t, which results in simply this answer here. And of course, that would be in square units. Okay, so we've looked at surface area, we've looked at arc length, and simply equations of slopes of tangent lines, the three objectives from this lesson. Hope it's been helpful.